Okay, so like I said, I'll be recording this and I'll post it because I am going to do a little lecture today. So if if you're not available at the moment for Mary, if you're working, you guys can do what you got to do, and then I'll be recording this so you guys can watch it later too. But it does help to watch. Yeah, that's fine. That's fine. If you guys are, if you, I see you guys are busy, so I'll just record it and you guys can watch it later, right? But don't. Okay. Yeah. Bye. But if you guys want to stick around and ask questions as I talk, then that helps too. Um, so the first thing is that uh, I want to see if you guys are willing and able to come on campus second semester. So we're allowed to have you guys, as you probably know, some of you guys can come on campus. We are allowed to have you guys on campus. It's just so I asked if I could do it for AP, and they said that I could do it during office hours. So we can't come during class times, but it'll be during office hours. So I'm going to send out this survey. Uh, I'm going to send out this survey, and I won't share what your answers are with anyone. So if you don't feel comfortable coming on campus, I totally understand and totally respect that. It will not be held against you in any way. Okay, so if you can't come on campus for whatever reason, that's fine. Okay, just select I'm not able to come on campus. I don't need a reason. I don't need an explanation. Whatever your reason is, that's your personal choice. Okay, totally understand. Totally cool with that. All right. For those of you who are willing and able to come on campus, it'll be during office hours. So it's either going to be Monday, Tuesday, Wednesday, or Friday during office hours. Thursday, we often have meetings. So I'm probably not going to do it on Thursdays. And during that time, we'll be doing the lab portions of the course. Okay. So we're supposed to do 16 labs. So basically, we'll be doing a lab a week, pretty much. That'll give us, if we do a lab a week, that'll give us 16 labs for in the second semester here. Be a little bit less than that, but maybe we can get 2 done in one day. At least some of the, like all the data done for like 2 or 3 labs in one day, and then you can take them home and finish them. And for those of you who cannot come on campus, what I'll do is I'll have those of you who can't come on campus collect the data, and then you can share the data, and then we'll just share the data with you guys, and and then you can do the labs that way with the data from either whoever's collected in class, or I'll give you like fake data, and then you can just do the lab that way. Okay, but it does. I think it's an important part of chemistry doing the labs. So if you can come in, to try and make that effort. And again, if you, I will never hold it against you if you can't come in for whatever reason. So if you can come in most Wednesdays or most Mondays, but maybe some you can't, just put Mondays down or Wednesdays down, and then the ones that you can't make, that's it is what it is, you know. It is what it is. Okay. Yeah, so that's the first thing. The second thing is the work from yesterday. Does anyone have any questions, any problems that you guys want me to go over from the work from yesterday? If you do have any questions that come up about the work from yesterday, please let me know, and I can make a video going over those answers. But yeah, I think it's pretty simple math stuff here. Some of it's not simple, but you know, some of it's tricky. So if there are ones that you want me to go over and explain, feel free to just email me, let me know, and I'll make a video and I can share it with the entire class. Okay. And I won't like divulge who asked me the question, or sometimes I will. But if you don't want me to divulge who asked the question, just say that. Just say that in your email. Say, hey, can you do this number? But please don't tell anyone that I asked. I know some people are a little shy, so that's okay. All right. So that was the work from yesterday. The work for today. The work for today is I'm going to go over these notes that I have here, and then you're just going to do the bookwork that I had assigned. Okay. I didn't put the bookwork answers up, but most of the odd numbers are included in the back of the book, and then some of them are not. So if there's some questions that you're unsure on, that you don't know if the answer is correct or not, then just ask me and I can go over it tomorrow or Monday. You know what I mean? Monday. But I probably won't put up answers per se for that. It's just kind of what I'll go over whatever you want me to go over. Okay. All right. So let's talk about the last part of the notes here. So there's really two things that I want to go over. We're first going to talk about the solution process. So what happens when solutions dissolve, or when solvents dissolve into when solvents dissolve into solutes dissolve into solvents. Let me do this for a second. Never mind. I was using this before because I'm sure you can hear that the saw going off in the background. Let me see if I can get my mic working again. Let's see, does that work? No, it does not work. Does that work? Yeah, but that's not the right one. No, and that doesn't work. All right. Anyway. Let me see. Sometimes if I disconnect and reconnect it, it works. Connected, voice and music. Disconnect. Connect. Connected, voice and music. Now, does that work? No, it doesn't work. Does that work? No, it doesn't work. All right. Anyway, I guess we'll just have to put up with that sound in the background. Sorry about that. Okay, so anyway, so first thing, again, we're going to talk about the energies associated with solution forming. It can be a little confusing, but I'll try and explain what's happening. And then we're going to talk about colligative properties. And again, these colligative properties, we're not going to be doing anything with the calculations for colligative properties. We're only doing the principles behind it. Okay, the principles behind it. All right, so let's talk first about this, the solution process. So in order for something to dissolve, right? So in order for something to dissolve, there really three things need to happen. The solvent, or sorry, the solute particles, their attractive forces have to break, right? You have to break apart the solute molecules. You also have to break apart the solvent molecules, and usually that takes energy, right? You need energy to break apart those bonds, those intermolecular forces. I shouldn't say bonds, the intermolecular forces, right? It takes energy to break apart the solvent molecules and break apart the solute particles. Okay, separate the IMFs. Okay, that always requires energy. Okay, then there's energy either released or absorbed when, or actually almost, it's always released. It's always, and then energy is released when the solvent and now the solute make intermolecular forces attractions with one another. Okay, so there's those three steps. Solvent breaks apart, solute breaks apart, solvent and solute come together. So those three things always have to happen. Okay. Now, those solvent particles and the solute particles, in order for them to break apart and come together, then the solvent solute to come together, the attractive forces between the solvent and solute have to be similar. They have to be similar to one another. Okay. So the intermolecular forces between solvent and solute have to be similar to those of the solvent solute. Have to be similar to one another. They don't have to be exactly the same, but they have to be alike. Okay, and that's where we get that term. We get that phrase like dissolves like. All right. So similar types of intermolecular forces dissolve one another. Okay. So that's what that's saying right there. Okay. And this is kind of a longer explanation of that, right? So water dissolves many salts because the ion dipole attractions water forms with the ions are similar. So you have a polar water molecule and an ion. The water molecule is very polar, so it basically has a positive and negative end, just like that ion that has a positive and a negative. Okay, so those attractions between the water and ion of the salt are very similar to the attraction between water and ion. All right. Whereas if you have a salt and hexane, hexane is is a nonpolar molecule. It only has London dispersion forces. Okay, so it does its attractions. The hexane attraction is much weaker than the ion attraction. Okay? And then the ion hexane attraction is very weak as well. Okay, so you won't have the salt ions going into solution in something like hexane. Same thing like oil and water don't dissolve. Oil has very weak London dispersion forces too. Whereas water has dipole attractions. Okay. So now oil, again, oil and water will have um, induced dipole attractions to one another. So that induced dipole is much weaker than the dipole attractions of water. So that induced dipole attraction again of oil with water is much weaker than that water bond. Okay, that's why oil and water do not mix. Okay, so they can't overcome the dipole hydrogen bonding. All right, that's basically why oil and water don't mix. Now, alcohol and water. Um, alcohol has an OH part on it, has an OH, so it can be slightly polar. Okay, it can be slightly polar. Um, now, if you now alcohol is just a long chain. It's just a chain of carbons with an OH at the end. Okay, that is what the definition of an alcohol: a chain of carbons with OH at the end. So there's all different types of alcohols. Okay, as you increase that chain of carbons, it becomes less and less polar. Okay, less and less polar because the molecule gets bigger and bigger, and the London dispersion forces start to overtake that polarity. The oxygen no longer pulls as much electron density towards itself, and the other side isn't as positive anymore. So yeah, the oxygen still will have a negative charge to it, but the other side won't be as positive because there's lots and lots of electron density on that side because there's lots of carbon atoms. So as the chain gets longer in alcohol, as it gets bigger and bigger, it gets less and less polar. So it gets less and less soluble in water. Okay. So alcohol can be soluble in water, like ethanol is very soluble in water. So is isopropyl. So is isopropanol. Okay. But as you get larger and larger alcohols, like something like octanol or something, 8 carbons long, or hexanol, like that becomes less and less soluble. So hexanol would be less soluble than something like methanol or ethanol or isopropyl alcohol, those kind of things. All right. Now, alcohol is can be soluble in non-polar solvents. So again, as the chain gets longer, it becomes more and more soluble in nonpolar solvents. So the most common nonpolar solvent is hexane. Hexane is the one that you're going to see the most of as a nonpolar solvent. Okay, so if you ever see hexane, it's C6H14. It's a nonpolar solvent, and it's a very common one. All right, alcohols are not very soluble, like short chain alcohols, ethanol, methanol, isopropyl alcohol. Those are not very soluble in hexanes. But as the chain gets longer, octanol, hexanol, heptanol, those ones are more and more soluble in nonpolar solvents, okay, because they become less and less polar. Okay, so again, with that idea of like dissolves like. All right, so let's get back to finding out or talking about what happens when something dissolves. Okay, so regardless of what type of solvent or solute you have, so in a salt, you're going to have that ion-ion bond breaking. Okay, don't worry, John. Okay, so in a salt, you're going to have that ion-ion bond breaking. But in something like soap or in alcohol, you're going to have the intermolecular forces breaking. All right. And then the solvent, you're always going to be having the intermolecular forces breaking. Okay. So the delta H here is the change in enthalpy, just like we talked about before, the change in enthalpy with thermochemistry. This is the same kind of thing. It takes energy. It always takes energy for these first two steps to break apart the solute and break apart the solvent, right? To break them apart, to expand them, to give them enough space so that that they can fit in between each other, right? So the the energy required, there's always going to be energy required to break apart those two things. Okay. Then the energy either input, it can be either there can be then energy is always released when you form the new bonds, the new intermolecular forces between the solvent and the solute. Okay, so it's always absorbed. It's always absorbed to break apart the bonds, and then it's released when you create the new bond, the new IMFs. I keep saying bonds, but I really should say IMFs. Right? Always absorbed, breaking the IMFs, and then released, creating the new IMFs. Now, the difference between these two things, the difference between this and this, determine whether the delta H of the entire solution, so the solvation process, whether the delta H of the solvation process is positive or endothermic, or negative exothermic. Okay, so this first one in A shows an exothermic, right? We're starting with a higher energy, we're winding up with a lower energy. Okay, so this is an exothermic solvation process. And this is an endothermic one, okay, where we have there's more energy required to break the bonds between solvent and solute and solute than is released when the new bonds between solvent and solute form. Okay. Now, again, so again, the delta H of solution is the energy released or absorbed when something dissolves. That's the definition of delta H of solution. Again, it can be positive endothermic or negative exothermic, all depending on the amount of energy released when the solvent-solute bonds form. IMFs, not bonds. IMFs, not bonds. Okay. Now, why would something, so it's obvious that something would dissolve, like reactions always occur, we want a lower energy state, right? If we think about our thermochemistry chapter, right? And we talked about free energy. Remember, reactions are thermodynamically favorable. We don't say spontaneous anymore, right? Reactions are thermodynamically favorable when the free energy is negative, right? When the free energy is negative, and free energy equals delta H minus T delta S, right? So if delta H is negative, that tells us, all right, yeah, most likely this is going to be, not only is delta H negative, but the entropy is always increasing when we when we dissolve something. Entropy is always going to increase when we dissolve something, right? We're going to get more disorder, right? We're getting more disorder. So if delta H is negative, delta S is positive, this will always be a spontaneous process, right? It'll always dissolve, right? Now, if delta H is positive, then the driving force of this solvation process must be the entropy, right? So it must be the entropy. Because delta H is positive, the only way to get a negative delta G is for delta S to be a larger factor than delta H. All right. Does that make sense to everybody? Kind of? Kind of. Oh, wait. Go back. I wanted to get my thing, but it's okay. Let me look at it here, actually. What was this called? Oh, I don't have it. Never mind. We'll just deal with it here. So, yeah. So remember, again, delta G is equal to delta H minus T delta S. If delta H is negative, then we don't even have to worry about delta S. Delta S in this case is positive because we're increasing the randomness of the system, right? We're increasing the entropy of the system, all right? If the delta H is positive, though, then we have to think, okay, delta H is positive, then the driving force of the solvation process must be the entropy, the increased randomness of the system. Okay. If something doesn't dissolve, then that must mean that the entropy, then that the delta H of solution is positive, and the delta S does not overcome it. The delta S does not overcome that process. So it takes too much energy to break the solvent and solute intermolecular forces, and then the amount of energy released when they come together is not great enough, or not great enough to overcome this and the delta S. Not overcome the delta S, but the delta S and this together are not enough. It causes the delta G to be negative. Okay. So this can be a little bit confusing, but remember, it's 3 steps. Breaking of the solute, breaking the solvent, creating that solvent-solute bond. 3 steps. All right. The first 2 steps always require energy put in. The last step always takes energy out. If the energy out is greater than the energy in, then the reaction will definitely happen. If the amount of energy going in is greater than the energy coming out, but the reaction still takes place, or the solution process still takes place, then the entropy is what's driving it. And that's enough. There's enough entropy change to drive the solvation process. Okay. I've seen this question on AP exams before. That's why I'm kind of going over it pretty in depth here, or I'm going over it multiple times. So make sure you kind of understand this and know how to draw it and understand what's like, draw these 3 steps and all that stuff. Okay, make sure you know how to do that. Okay. So that's what it says here. I just was saying it there. So it's written here if you forget. Right. Same thing here. This is all what I just said. Okay. So if you forget, it's all written there. You can read it again. Okay, so let's talk about colligative properties. So I'm going to talk about each one of the colligative properties alone, but just this is like a little bit. I'm going to show you this in the beginning and show you it at the end. Okay, All these properties that I'm going to talk about right now, they're all dependent on the number of solute particles in solution. So the more particles in solution, the greater the extent of the change of the property. And you're going to understand what that means in a second. And then the type or size of the particles don't matter. It doesn't matter what type of particles there are. It doesn't matter how many. It doesn't matter the size of them. The only thing that matters is how many. How many. Okay, so the first one is vapor pressure lowering. So a solution that has a non-volatile solute always has a lower vapor pressure than the pure solvent. So basically, if you add salt to water, you're going to lower the vapor pressure, which in turn increases the boiling point. Okay. Now, one of the reasons for this, if you look here at the surface of the solvent, you'll see that the ions now are at the surface. So again, this is another exam question that I've seen in the past, that they ask, why does the vapor pressure lower, or why do any of these things change? And it's all the same. It's all the same. The solute particles interfere with the property. Okay, so here the solute particles take place of some of the solvent particles at the surface. Okay, and vapor pressure is the evaporation of the solvent particles at the surface, right? So if these solute particles are there, then the solvent particles cannot evaporate. Okay, so you're just not going to have as many solvent particles at the surface. Since there's not as many solvent particles at the surface, not as many of them will evaporate. Okay, so you're going to get a lower vapor pressure. Okay, so again, the solute particles interfere with the evaporation of the solvent. They kind of get in the way. They get in the way. The solvent particles are trying to get to the gas phase, but these other particles, the solute particles, are getting in the way. They're taking their place. Okay. Now, if the vapor pressure lowers, that means that the boiling point will elevate. So I'm going to go to this one because this one makes more sense. So the boiling point will be higher now because the vapor pressure is lower. And if you recall, boiling point is when vapor pressure equals atmospheric pressure. So if vapor pressure is lowering, that means you have to have a higher temperature in order to reach atmospheric pressure. Okay, so solution always has a higher boiling point than the pure solvent. Okay, so the more solute particles, the higher the boiling point. If you add salt to water, you'll increase the boiling point. You'll increase the boiling point. All right, again, and the reason for that is that those particles just get in the way. They get in the way. They don't allow the evaporation of the solvent. Okay? So vapor pressure lowering and boiling point elevation go hand in hand. They're like, you lower the vapor pressure, you're going to increase the boiling point. Pretty much that's what's going to happen. Okay. The reason the vapor pressure lowers is because those particles get in the way. Now for freezing point actually gets lower. Okay, so the freezing point goes down. Okay, the more solute particles you have, the lower the freezing point. And again, the same, a very similar reason what we said before is those solute particles get in between the solvent particles and disrupt those intermolecular forces. So in order for something to freeze, the intermolecular forces have to hold the particles together in a solid state. Okay. Now, if you have solute particles in there getting in the way, it makes it much, much harder for it to freeze. Okay. It makes it harder for those intermolecular forces to solidify that substance into a solid. Okay. So it's important you understand not only that these things occur, but why they occur. So vapor pressure lowering, particles get in the way at the surface, prevent evaporation. Freezing point depression, the solute particles get in the way of the solvent intermolecular forces. Okay, so you need to lower the temperature even further for that solid to form. All right. And then boiling point goes up again because the vapor pressure goes down. Okay. And finally, just a reminder, again, all these properties are dependent on the number of solute particles. It has nothing to do with the type or size of particles, just the number. So the more particles you have in solution, the greater the extent of change. Okay. One of the most common questions on here is something like this. So I'll do it here. So which one would have a greater change in boiling point? 1 molar, so let's say 1 liter of 1 molar NaCl, or 1 liter of 1 molar CaCl2. If both of these were dissolved in water, which one would have a greater change in the boiling point, or the greater change in freezing point? Well, if you think about it, NaCl breaks up into Na plus and Cl minus. So there's 2 particles for every one of these, right? This one, though, breaks up into Ca, 2 plus, and then Cl minus and Cl minus. Okay, so this one is going to have a greater effect on colligative properties because more ions in solution. Okay, so whatever one puts more ions in solution is going to have the greater effect. Okay, it gets tricky if they were to say if they were to change these, you'd actually have to calculate the actual number of ions, the concentration of ions in solution. But this would be like 1 molar, 1 molar, 1 molar. So this would be a total of 3 molar ions in solution. Okay, you'd add them all up. Now, if you changed it, let's just say if you did, let's see here. Let's make this 0.75 instead. So that means you'd have 0.75 plus 0.75 plus 0.75. Okay, this would be 1 molar, and this would be 1 molar. So this is total 2 molar, and this is 2.25. So this is still greater. Even though this concentration is less, this is still greater because you have to multiply by 3. Okay, each one of these would be 0.75, 0.75, 0.75, but really in reality, this is Cl2 is 1.5, right? It's 1.5 plus 2.75. Okay, but I like thinking about it this way. Okay, so I think there might be some problems like that in the future. Okay, and that is all I had for you guys today. You guys have any questions? No?